A treatise on the Node.js package management ecosystem. Concepts and internals for the advanced technical interview. Introduction. The Node.js ecosystem is defined by its vast and dynamic repository of open-source packages, managed primarily through the Node Package Manager, NPM. At a surface level, developers interact with this system through simple commands like npm install. However, a superficial understanding of these tools belies the intricate and evolving architecture that underpins modern JavaScript development. For the senior software engineer, a deep, conceptual mastery of this ecosystem is not merely advantageous. It is essential. This knowledge transcends trivia, serving as a direct indicator of an engineer's ability to reason about software architecture, stability, security, and scalability. This report provides an exhaustive exploration of the minutiae of Node.js package management, tailored for the advanced technical interview. It deconstructs the core components of the NPM toolkit, from the foundational package.json manifest to the complexities of module resolution and the nuances of TypeScript integration. The narrative follows the historical and logical evolution of the ecosystem, demonstrating how each new feature, be it the package.lock.json file, the exports field, or the npm CI command, was developed in response to the real-world challenges of building reliable software at scale. Understanding this evolution is critical. The journey from a convention-based model to a more explicit contract-based system reveals fundamental principles of software engineering. It illustrates the inherent tension between flexibility and stability, the critical importance of deterministic builds, and the pragmatic solutions required to bridge the gap between typed and untyped worlds. An engineer who can articulate not just what these tools do, but why they exist and the problems they solve, demonstrates a level of maturity and insight that is the hallmark of a top-tier candidate. This report aims to equip you with that foundational understanding, enabling you to navigate the most demanding technical discussions with confidence and authority. Section 1. The Anatomy of a Node.js Package. At the heart of every Node.js project and library lies the package.json file. It is far more than a simple metadata file. It is the foundational contract that defines a package's identity, its relationship with the broader ecosystem, and its public-facing API. A comprehensive understanding of its structure and the semantic purpose of its fields is the first step toward mastering Node.js package management. 1.1. The package.json manifest. A package's identity. The package.json file serves as the manifest for any Node.js project, containing essential metadata that NPM uses to identify the package and manage its dependencies. For any package intended for publication on the NPM registry, two fields are not just important, but mandatory: name and version, core identifiers. The name and version fields, when combined, form a globally unique identifier within the NPM registry. This uniqueness is the bedrock upon which the entire package resolution system is built. Any change to the package's code that is intended for distribution should be accompanied by a corresponding increment in the version. The name field is subject to a set of rules to ensure compatibility and avoid ambiguity across the ecosystem. It must be 214 characters or less, cannot contain uppercase letters, and must not include any non-URL safe characters, as the name is often used in URLs, command line arguments, and folder names. To avoid conflicts with Node.js's built-in modules, it is best practice not to use the name of a core module. A significant feature for organization and namespacing is the use of scoped packages. A name can be prefixed with a scope, such as at my org/my package, which helps group related packages and prevent naming collisions in the public registry. Descriptive metadata. Beyond the core identifiers, package.json contains several fields that are vital for discoverability, legal compliance, and community interaction. Fields like description and keywords are indexed by the npm search command, making it easier for other developers to find your package. The homepage field provides a link to the project's main page, while the bugs field can direct users to the issue tracker, a functionality leveraged by the npm bugs command. For legal clarity, the license field should specify the software license under which the package is released, using standard SPDX identifiers, e.g. ISC or MIT or GPL 3.0. Furthermore, the funding field allows authors to provide information on how users can financially support the project's development, which can be accessed via the npm fund command. 1.2. Defining the public API. From main to exports. A package's contract extends to defining how it can be consumed. This is managed through fields that declare the package's entry points. The evolution of these fields, from the simple main property to the powerful exports, map, marks a significant maturation of the Node.js module system. The legacy main field. For many years, the main field was the sole, conventional method for declaring a package's primary entry point. It is a simple string that specifies the path to a single file, which by convention was the common JS entry point for the package. When a user wrote, "require my package," Node.js would consult this field to determine which file to load. The rise of the exports field. The simplicity of the main field became a liability with the rise of modern JavaScript. The ecosystem now needed to support multiple module formats, primarily CommonJS, require, and ES modules, import, and different runtime environments such as Node.js and the browser. The exports field was introduced in Node.js version 12 to address this complexity, providing a powerful and explicit mechanism to define a package's entry points. A critical and intentional consequence of using the exports field is the enforcement of encapsulation. When exports is present in a package.json, it acts as a definitive list of the package's public API. Only the paths defined within the exports map are accessible to consumers. Any attempt to import or require an internal file that is not explicitly exposed, such as require my package internal utils.js, will result in a module not found error. While this is a breaking change from the older, more permissive model, it is a crucial feature. It allows package authors to safely refactor internal code and manage their dependencies without the risk of users relying on private implementation details, thereby creating a more stable and maintainable ecosystem. The most powerful feature of exports is its support for conditional exports. This allows a single package to expose different files based on the consumer's environment or module system. The primary use case is to provide distinct entry points for CommonJS and ES modules consumers. This is done by mapping condition names such as require and import to their respective file paths. The default condition serves as a fallback for unknown environments, ensuring forward compatibility. Furthermore, the exports field supports subpath exports, allowing a package to define multiple named entry points beyond the main .export. This enables consumers to use cleaner, more intuitive import paths like import submodule from my package, submodule, instead of a more verbose path like import submodule from my package, dist, submodule. This improves the developer experience for the consumer while allowing the package author to maintain an organized internal directory structure. For TypeScript projects, the exports field introduces specific requirements. To correctly resolve the types for a package that uses exports, a consuming project must set module resolution, Node 16, or Node Next in its TIA's config.json file. Moreover, the package author must provide corresponding type definition files, .d, .ts for common.js, .d, .mts for ES modules for each entry point. Critically, within the conditional exports map, the types condition must be listed before the implementation conditions import and require for the TypeScript compiler to resolve them correctly. 1.3. The spectrum of dependencies, a conceptual breakdown. The different dependency types listed in package.json are not merely organizational conveniences. They represent distinct semantic roles that a package can play throughout the software development lifecycle. Understanding these roles is key to architecting robust and efficient applications. Dependencies. These are the packages that are essential for the application to function in a production environment. They represent the core libraries and frameworks that your code directly imports or requires to execute its primary logic, such as Express for a web server or React for a user interface. These packages are installed by default when a user runs npm install and are included in the final production bundle. Dev dependencies. These packages are necessary only during the development and build phases of a project. This category includes tools for testing, e.g., jest, linting, and code formatting, e.g., ESLint, Prettier, and bundling, e.g., Webpack, Rollup. They are not required for the application to run in production. By separating these tools into dev dependencies, they can be excluded from a production installation by using the npm install -- production flag, which results in a smaller, more secure, and faster to deploy application artifact. Peer dependencies. This is one of the most critical and often misunderstood dependency types, particularly for library authors. A peer dependency is a declaration of compatibility. It specifies a package that your library expects the host application to provide. It does not cause the package to be installed. Instead, it creates a contract between your library, the plugin, and the consumer's project, the host. The canonical example is a React component library. The library needs React to function, but it should not bundle its own copy of React. Doing so would lead to two separate instances of React in the final application, one from the host and one from the library, causing state inconsistencies and errors. By declaring React as a peer dependency, the library signals that it is compatible with a certain version range of React and relies on the host project to supply it. The way npm handles unmet peer dependencies has evolved. Prior to version 4, they were installed automatically. From versions 4 through 6, npm issued a warning, prompting the developer to install them manually. Modern versions of npm are stricter, often treating unmet peer dependencies as an error, reflecting their importance for package compatibility. To facilitate local development and testing of a library, it is a common and recommended practice to also list the peer dependencies in the dev dependencies section. Optional dependencies. As the name implies, these dependencies are not mandatory for the application to run. If an optional dependency fails to install for any reason, such as a platform-specific incompatibility, NPM will not terminate the installation process. It is then the responsibility of the application code to handle the absence of this package gracefully. This is typically achieved by wrapping the require function call or import function call in a try.catch block, allowing the application to function without the enhanced feature provided by the optional package. Bundled dependencies. This field, which can also be spelled bundle dependencies, takes an array of package names that will be packed directly into the project's tarball when npm pack is run or when the package is published. Unlike regular dependencies that are fetched from the npm registry upon installation, bundled dependencies are included with the package itself. This is useful for several niche scenarios: when a dependency is not available on the npm registry, when you're using a locally modified version of a third-party library, or when you need to ensure that specific dependencies are available in an offline environment. Section 2. Versioning and deterministic installations. The stability and reproducibility of a Node.js project hinge on two core mechanisms: a disciplined approach to versioning and a robust system for locking down the dependency tree. The interplay between the flexibility of semantic versioning in package.json and the rigidity of the package lock.json file is a central theme in modern package management. This system is a direct response to the classic software engineering trade-off between the desire to incorporate updates and the need to prevent unexpected breakages. 2.1. The nuances of semantic versioning. SEMVer. Semantic versioning, or SEMVer, is a formal convention for specifying version numbers that is designed to convey meaning about the underlying code and the nature of changes from one version to the next. The standard format is major.minor.patch. Major. Incremented for incompatible API changes that will likely break existing code. Minor. Incremented for new, backward-compatible functionality. Patch. Incremented for backward-compatible bug fixes. In package.json, developers rarely pin dependencies to an exact version. Instead, they use special range operators to express their tolerance for updates. The two most common operators are the caret and the tilde. The caret operator. The caret is the default operator used by npm when you run a command like npm install -save. It signifies a compatibility range that allows for updates to both the minor and patch versions, but freezes the major version. For example, a dependency specified as 1.2.3 will match any version from 1.2.3 up to, but not including 2.0.0. This approach is generally preferred for application development because it represents a balanced trade-off. It allows the project to automatically receive new features and security fixes, minor and patch releases, while protecting against breaking changes, major releases. The tilde operator. The tilde is a more restrictive operator. It locks both the major and minor versions, allowing only patch-level updates. For example, 1.2.3 will match any version from 1.2.3 up to, but not including 1.30. This operator is often favored by library authors for their own dependencies. By limiting updates to only bug fixes, it provides a higher degree of stability and predictability, minimizing the risk that a transitive dependency update could inadvertently break the library for its consumers. The magic zero anomaly. A crucial and often tested nuance of SEMVer in npm is the special handling of versions below 1.00. According to the Semver specification, versions starting with 0, e.g. 0.x.y, are considered unstable, and any change could be a breaking one. The caret operator respects this convention with more restrictive behavior. For a version like caret 0.2.3, the caret behaves identically to a tilde 0.2.3, allowing only patch updates. It will match versions up to, but not including, 0.3.0. For a version like 0.0.03, the caret allows no updates at all, effectively pinning the dependency to the exact version 0.0.03. This magic zero behavior is a safeguard against the inherent instability of pre-release software, ensuring that developers do not accidentally pull in breaking changes from dependencies that have not yet reached a stable 1.00 milestone. 2.2. The lock file as a deterministic blueprint. While the flexibility of Semver ranges in package.json is beneficial for staying current, it is also the direct cause of non-deterministic builds. If two developers run npm install on the same project at different times, the Semver ranges could resolve to different patch or minor versions of the same dependency. This can lead to subtle bugs and the classic "it works on my machine" problem, a significant source of friction in collaborative development and deployment pipelines. The solution: package-lock.json. The package-lock.json file is automatically generated or updated by npm to solve this problem of non-determinism. It acts as a complete and precise snapshot of the dependency tree at a specific moment in time. It records the exact version of every single package that was installed, including not only the direct dependencies listed in package.json, but also all of their transitive, nested dependencies. The structure of the lock file contains critical information for ensuring reproducibility. Key fields include :name and version, the identity of the root package. Lock file version, an integer indicating the format of the lock file itself, which has evolved across npm versions. Resolved, the exact URL from which the package's tarball was downloaded. Integrity, a sub-resource integrity, SRI, hash, typically SHA-512 of the package's contents. This integrity hash is a vital security feature. During installation, npm verifies that the downloaded package's hash matches the one stored in the lock file. This protects against supply chain attacks, where a malicious actor might compromise a package on the registry and replace its code without changing the version number. Without this integrity check, a project could unknowingly install malicious code. With it, the installation will fail, alerting the developer to the discrepancy. By committing the package-lock.json file to source control, a project guarantees that every developer, every continuous integration, CI, build, and every production deployment will generate an identical node modules tree, thus achieving fully reproducible and deterministic builds. Furthermore, since npm version 7, the lock file has been optimized to contain enough information to build a complete picture of the dependency tree on its own, reducing the need to read numerous package.json files from within Node modules and significantly improving installation performance. 2.3. Installation strategies: npm install versus npm CI. The existence of both a flexible package.json and a rigid package-lock.json necessitates distinct installation commands tailored for different phases of the development lifecycle. npm install and npm CI provide explicit control over the trade-off between flexibility and stability. npm install. This is the versatile general-purpose command for managing dependencies in a development environment. Its behavior is adaptive. It reads the semver ranges from package.json to understand the developer's intent. It then consults package lock.json. If the lock file is present and consistent with package.json, it will install the exact version specified in the lock file. Crucially, if package.json is modified, e.g., a dependency is added or a version range is updated, npm install will resolve the new dependency tree, fetch the appropriate packages, and update the package.lock.json file to reflect this new state. This mutable behavior makes npm install the ideal tool for the active development phase, where dependencies are frequently added, removed, or updated. npm ci, clean install. This command is purpose-built for automated environments where predictability, speed, and reliability are paramount, such as CI/CD pipelines, testing platforms, and production deployments. Its behavior is intentionally strict and immutable. Strictness and validation. npm ci requires a package lock.json or npm shrinkwrap.json file to exist. It uses this lock file as the single source of truth. If the dependencies listed in package.json are out of sync with the lock file, npm ci will not attempt to resolve the conflict. It will exit with an error. Immutability. It will never write to or modify package.json or packagelock.json. The installation is completely frozen, based on the committed lock file. Clean slate installation. Before beginning the installation, npm ci will first completely remove any existing Node modules directory. This ensures that the installation starts from a clean, known state, eliminating any potential artifacts from previous builds. Performance. npm ci is significantly faster than npm install in automated contexts. Because it does not need to perform complex dependency resolution or calculate a new dependency tree, it can skip directly to downloading and linking the exact packages defined in the lock file. In summary, the best practice is to use npm install during local development to manage dependencies and npm ci in all automated environments to ensure fast, reliable, and perfectly reproducible builds. Section 3. The Module Resolution Labyrinth. One of the most fundamental processes in a Node.js application is module resolution, the algorithm Node.js uses to locate and load the code specified in an import or require function call statement. This process is not magic. It is a deterministic state machine with a clear set of rules. A deep understanding of this algorithm is a practical, high-value skill that allows an engineer to effectively debug module not found errors and reason about the structure of a project. 3.1. The core algorithm. How Node.js finds code. When a module is requested, Node.js follows a strict hierarchical sequence of checks to find the corresponding file or package. Step 1. Core modules. The first check is always against Node.js's list of built-in core modules. If the module identifier matches a core module, e.g., fs, path, http, Node.js returns the internal module and the resolution process stops immediately. Core modules can also be explicitly requested using the node : prefix, such as node:/fs, which makes it clear that a core module is intended. Step 2. Relative or absolute paths. If the module identifier is not a core module, Node.js checks if it begins with slash, dot slash, or dot slash. If it does, the identifier is treated as a file system path. If the path is absolute, starts with slash, Node.js will look for the module starting from the root of the file system. If the path is relative, starts with dot slash or dot dot slash, Node.js will search for the module relative to the location of the file that is making the require function call or import call. When resolving a path, Node.js performs the following checks in order. As a file, if the path points to a file, Node.js attempts to load it. If no file extension is provided, it will try appending .js, then .json, which is passed as a JSON text file, and finally .node, which is loaded as a compiled binary add-on. As a directory, if the path points to a directory, Node.js will look for a package.json file inside that directory. If found, it will try to load the file specified in the main field, or in modern Node.js, resolve via the exports field. If there is no package.json or no main exports field, Node.js will fall back to looking for an index.js, then an index.json, and finally an index.node file within that directory. If any of these checks succeed, the module is loaded and the process ends. If all fail, an error is thrown. Step 3. Node modules. Traversal. If the module identifier is a bare specifier, meaning it is not a core module and does not start with a path prefix, e.g., lodash, express, Node JavaScript initiates its node modules lookup algorithm. This recursive process is the cornerstone of how NPM dependencies are made available to an application. The algorithm works as follows. Node.js starts in the parent directory of the current file, the one containing the require source import statement. It appends /node modules to this path and attempts to resolve the module identifier from within that directory, using the same file directory logic described in step 2. If the module is not found, Node.js moves one level up the directory tree to the parent's parent directory. It repeats step 2 and 3, walking up the directory structure, checking a node modules folder at each level, until it either finds the module or reaches the root of the file system. This upward traversing algorithm is what allows a package installed in the root node modules of a project to be accessible from any file within that project, regardless of its nesting depth. It is also the mechanism that enables dependency hoisting, where package managers place shared dependencies as high up in the tree as possible to avoid duplication. 3.2. The duality of module systems, CommonJS and ES modules. Node.js historically used its own module system, CommonJS, but has since adopted the official JavaScript standard, ES modules. Modern Node.js supports both systems, but their fundamental differences create a complex seam that developers must understand. CommonJS. CommonJS. CommonJS is the original module system of Node.js, characterized by the synchronous require function call function for importing modules and the module.exports or exports objects for exporting them. Its synchronous nature means that when require function call is called, the event loop is blocked until the module is found, loaded, and executed. This allows modules to be required from anywhere within a function or block of code. ES modules. ES modules. ES modules are the official standard for JavaScript defined by the ECMAScript specification. They use the import and export keywords. The key difference is that ES modules loading is asynchronous. This allows for features like top level, await, and enables more effective static analysis and tree shaking by bundlers. Determining the module system. Node.js uses a set of explicit rules to determine whether a given file should be treated as CommonJS or ES modules. File extension. This is the most explicit signal. Files ending in .mjs are always treated as ES modules. Files ending in .cjs are always treated as CommonJS. Package.json type field. For files with a .js extension, Node.js looks for the nearest parent package.json file. If that file contains type module, all .js files within that package's scope are treated as ES modules. If the package.json contains type CommonJS, or if the type field is absent, .js files are treated as CommonJS by default. Interoperability rules. The interaction between these two systems is a common source of confusion and errors. The rules are strict and based on the synchronous versus asynchronous nature of the loaders. Importing CommonJS from ES modules. An ES module can import a CommonJS module. When this happens, the entire module exports object from the CommonJS module is made available as the default export to the ES modules module. Node.js also performs static analysis on the CommonJS code to try and identify named exports, making them available as a convenience. But this process is a heuristic and not always reliable. Importing ES modules from CommonJS. A CommonJS module cannot use the synchronous require function call function to load an ES module. This is because ES module's loading is asynchronous, and require function call cannot return a value that has not been loaded yet. The correct way for a CommonJS module to load an ES modules module is to use the dynamic import function call function, which returns a promise that resolves with the module's namespace object. 3.3 TypeScript's mirror. Type-level resolution. TypeScript's module resolution system is not an independent invention. It is designed to be a type-level simulation of the module resolution system of the target runtime environment. Its primary goal is to find the correct type definition files, .d, .ts, that correspond to the JavaScript modules that will be loaded at runtime. This allows TypeScript to provide accurate static type checking and editor IntelliSense. The module resolution option in the tsconfig.json file is the key to configuring this behavior. Node 10 or Node. This mode mimics the resolution algorithm of older CommonJS-only versions of Node.js. It supports features like resolving index.js files from directories and omitting file extensions in import paths. Node 16/Node Next. These are the modern recommended settings for Node.js projects. They accurately model the dual CommonJS/ES modules module system. For example, when using Node 16, TypeScript will enforce Node.js's own rule that import statements for relative paths in ES modules files must include the file extension, e.g. import./utils.js, while require calls in CommonJS files do not have this restriction. Bundler. This is a newer resolution strategy designed to model the behavior of modern bundlers like Webpack, Vite, or sbuild. These tools often use a Node.js-like resolution algorithm, but may have slightly different rules, such as allowing extensionless imports even for ES modules, which this mode accommodates. In addition to module resolution, the base URL and paths options in tsconfig.json allow developers to create type-safe aliases for module paths. The TypeScript compiler will resolve these aliases first Before falling back to the standard Node modules, lookup algorithm, enabling cleaner and more maintainable import paths in large projects. Section 4. The TypeScript integration layer. The immense success of TypeScript is due in large part to its ability to seamlessly integrate with the existing JavaScript ecosystem, which is predominantly untyped. This integration is not magic. It is a well-designed system built upon declaration files and a vast, community-driven repository of type definitions. Understanding this layer is crucial for any developer working with TypeScript in a Node.js environment. 4.1. The role of declaration files. .d.ts. JavaScript is a dynamically typed language, meaning the type of a variable is determined at runtime. TypeScript, conversely, is a statically typed language, providing type checking at compile time. This creates a fundamental gap. How can the TypeScript compiler understand the structure of a plain JavaScript library to check for errors and provide assistance? The answer lies in declaration files, which have a .d.ts extension. These files serve as a bridge between the typed world of TypeScript and the untyped world of JavaScript. A .d.ts file contains only type information. It has no implementation code or executable logic. It acts as a contract or a blueprint that describes the shape of a JavaScript module to the TypeScript compiler. It declares the functions, classes, objects, and variables that the library exports, along with their corresponding types. For example, a declaration file for a simple JavaScript utility might look like this: declare module myJSLib, export function, sum function, arg string, number. This tells the TypeScript compiler that the myJSLib module has an exported function named sum function that takes a string and returns a number. With this information, the compiler can perform two critical tasks. Static type checking. If a developer tries to call some function 123, passing a number instead of a string, the compiler will flag it as an error before the code is ever run. Editor tooling. IntelliSense. Modern code editors leverage this type information to provide powerful features like auto-completion, parameter info, and go-to-definition, dramatically improving the developer experience. 4.2. The @types ecosystem, and definitely typed. In an ideal world, every JavaScript library author would provide their own .d.ts file bundled with their npm package. While this is becoming more common, the reality is that the vast majority of packages on npm do not include them. To solve this problem, the TypeScript community created Definitely Typed, a massive, centralized open-source repository that hosts high-quality, community-maintained type definitions for thousands of JavaScript libraries. The type definitions from the Definitely Typed repository are automatically published to the npm registry under the @types scope. So if you need type definitions for a popular library like Lodash or Express, you can install them with a simple npm command, npm install, savedev @types/Lodash. The TypeScript compiler is specifically designed to work with this ecosystem. By default, it is hardwired to automatically look for type definitions in the node modules @types directory. When your code contains an import statement like import as from Lodash, the compiler will not only look for the Lodash package itself, but will also automatically discover and load the corresponding type definitions from node modules @types Lodash index.d.ts. This provides a seamless zero-config experience for consuming types for most popular packages. 4.3a Critical distinction. at types in dependencies versus dev dependencies. One of the most nuanced and frequently asked interview questions regarding TypeScript and NPM revolves around whether at-types packages should be saved as dependencies or dev dependencies. The correct answer depends entirely on whether you are building an application or a library. The general rule: applications use dev dependencies. For a final application, e.g., a web server, a command line tool for internal use, at-types packages should almost always be placed in dev dependencies. The reasoning is straightforward. Types are a development time construct. They are used by the TypeScript compiler TSC to perform static analysis and catch potential errors. During the build process, the TypeScript code is transpiled into plain JavaScript, and all type annotations are erased. The final running JavaScript code has no knowledge of TypeScript types and therefore has no runtime dependency on the at-types packages. Placing them in dev dependencies ensures they are available for development and building, but are not included in the final production deployment, keeping the production artifact lean. The exception: libraries use dependencies. This is the critical exception that distinguishes a senior-level understanding. If you are authoring a library that will be published to NPM for other developers to consume, and your library's public API exposes types from another package, then the corresponding at-types package must be listed in your dependencies. To understand why, consider the perspective of the library's consumer. When you publish your TypeScript library, you typically include a generated .d.ts file that describes your library's public API. Imagine your library has a function like this: import, request, response, from express, export function, myExpress. Middleware, rec, request, res, response, void. The generated mylibrary.d.ts file will contain a reference to the types from express: import type, request, response, from express. When a developer installs your library in their own project, their TypeScript compiler needs to understand the types request and response to correctly type check their usage of your myExpress middleware function. If you had listed @types/express as a dev dependency, it would not have been installed for the consumer. Their compiler would be unable to find the definitions for request and response, and their build would fail with a type error. By placing @types/express in your dependencies, you ensure that the necessary type definitions are installed alongside your library for the consumer, allowing their TypeScript compiler to correctly resolve the types and understand your library's API. This distinction demonstrates a deep understanding of the difference between an application's internal implementation and a library's public contract. Section 5. The broader NPM toolkit and ecosystem. Beyond the core functionalities of defining and installing dependencies, the NPM ecosystem provides a rich set of tools for executing packages, ensuring security, and managing complex project structures. Furthermore, the landscape is not monolithic. Competing package managers have emerged, each offering a different philosophical and technical approach to solving the challenges of dependency management. A comprehensive understanding of this broader context is vital for making informed architectural decisions. 5.1 NPX, the Package Executor. NPX, which stands for Node Package Execute, is a command line tool bundled with NPM since version 5.2.0 that fundamentally changes how developers interact with package executables. Its primary purpose is to run commands from NPM packages, without needing to install them globally or manage local paths. The workflow of npx is simple yet powerful. When you run a command like npx, it performs the following steps. It first checks if the command's executable exists in the local project's node modules.bin directory. If it does, npx executes it directly using the project's locally installed version. If the command is not found locally, npx will temporarily download the latest version of the corresponding package from the npm registry into a cache. It then executes the command from this temporary location. After the command finishes, npx cleans up the temporary installation, leaving no permanent packages on your system. This behavior makes npx exceptionally useful for two main scenarios. One-off commands. For tools that are used infrequently, npx avoids the need to clutter the global namespace with npm install -g. A prime example is scaffolding a new project with npx create react app my app. This ensures you are always using the most up-to-date version of the scaffolding tool without a persistent installation. Running local binaries. It simplifies running executables provided by a project's local dependencies. Instead of typing ./node modules/.bin/lint, a developer can simply run npx slint. In essence, npx is a tool for execution, whereas npm install is a tool for installation. 5.2 npm audit, a built-in security sentinel. As modern applications increasingly rely on hundreds or thousands of third-party dependencies, security has become a paramount concern. npm audit is a built-in command designed to help developers identify and mitigate security vulnerabilities within their dependency tree. When you run npm audit, it performs the following actions. It creates a description of your project's complete dependency tree, as defined in your package lock.json file. It submits this description to a vulnerability database, currently the GitHub Advisory database. It receives a report of any known vulnerabilities found in the versions of the packages you are using. The audit report provides detailed information for each vulnerability, including its severity level, low, moderate, high, or critical, a description of the vulnerability, the affected package, and the specific dependency path that introduced the vulnerable package into your project. To help with remediation, npm provides the npm audit fix command. This command will attempt to automatically resolve the reported vulnerabilities by updating the affected packages to a non-vulnerable version. If one is available within the Semver range specified in your package.json, it effectively runs an npm install under the hood and updates your package lock.json. If a fix requires a major version bump, a potentially breaking change, the double -force flag is required. This should be used with extreme caution, as it can introduce breaking changes into your application. It's important to note the limitations of npm audit. It does not scan peer dependencies, and it can sometimes produce a high volume of noise by reporting on vulnerabilities in dev dependencies, which are typically not included in the final production application and may pose a lower risk. 5.3. A comparative analysis of package managers. The dominance of npm has been challenged over the years by alternative package managers, each born from a desire to solve the perceived shortcomings of the original. The evolution of these tools reflects a broader industry-wide push for better performance, efficiency, and reliability. The primary battleground has been the design and management of the Node modules directory, npm. As the default package manager bundled with Node.js, npm is the most widely used. Early versions were plagued by slow performance and non-deterministic installs, while it has improved dramatically, adopting a lock file and parallel installations. Its fundamental approach to creating a flattened node modules directory can still lead to significant disk space usage and slower installation times compared to its modern counterparts. Yarn Classic Version 1. Yarn was created by Facebook in 2016 to address NPM's early failings. It introduced key innovations that are now standard, such as a deterministic lock file, .yarn, .lock, and parallel package installation, which made it significantly faster and more reliable than the NPM of its time. However, Yarn Classic still uses the same flattened node modules architecture as NPM, inheriting some of its inefficiencies. Yarn Berry version 2 and above. Yarn Berry represents a radical rethinking of package management. Its flagship feature is plug-and-play (PNP), an architecture that completely eliminates the node modules directory. Instead of extracting thousands of files to disk, Yarn Berry stores packages as compressed archives, e.g., .zip files, in a .yarn/cache folder. It then generates a single .pnp.cjs file that contains a map, telling Node.js exactly how to resolve require function call calls by loading code directly from these compressed archives. This approach results in extremely fast installations. The I/O overhead of creating the node modules directory is eliminated. Enhanced efficiency. Disk space usage is drastically reduced. Stricter dependency enforcement. Packages cannot access phantom dependencies that they haven't explicitly declared. Zero installs. The .yarn/cache can be committed to the repository, allowing CI/CD pipelines to skip the installation step entirely. The main drawback is that some tools that make assumptions about the existence of a node modules directory may not be compatible with PNP without configuration changes. PNPM. PNPM, Performant NPM, offers a third, highly innovative solution. It addresses the node modules problem, not by eliminating it, but by re-architecting it using links. PNPM maintains a single, global, content-addressable store on the developer's machine. When a package is installed in a project, PNPM does not copy the files. Instead, it hard links the files from the global store into the project's node modules .pnpm directory. Then, it uses symbolic links, symlinks, to create the nested dependency graph that Node.js expects. This architecture provides the best of both worlds, maximum disk space efficiency. A package's files exist only once on the disk, no matter how many projects use it. Blazing fast installations. Linking is significantly faster than copying files. Strictness. The symlinked node module structure is not flat, which prevents packages from accessing undeclared phantom dependencies, a common source of bugs. The following table provides a high-level comparison of these package managers. Feature NPM Yarn Classic version 1, Yarn Berry version 2 and above, PNPM. Node modules, structure flattened with potential duplication. Flattened with potential duplication. Plug and play, no node modules. Symlinked from a global content addressable store. Lock file package. Lock.json yarn. Lock yarn.lock. PNPM lock.yml. Core strength default. Built-in universal compatibility. Early performance, determinism improvements, zero installs, strictness, extreme speed, disk space and installation speed efficiency. Strictness. Key weakness, historically slower, less efficient legacy, superseded by berry compatibility issues with tools expecting Node modules, learning curve for symlink-based structure. 5.4. Managing monorepos with workspaces. A monorepo is a software development strategy where code for many different projects is stored in the same repository. This approach is increasingly popular for its benefits in code sharing and atomic cross-project changes. However, it presents significant challenges for dependency management. Workspaces are the package manager feature designed to solve these challenges. Supported by modern versions of NPM, Yarn, and PNPM, workspaces provide a streamlined way to manage multiple packages within a single root project. The configuration is typically done in the root package.json for NPM and Yarn, or a PNPM workspace.yaml file for PNPM, where you define the paths to your individual packages, e.g., packages/star. When you run install from the root of a workspace-enabled project, the package manager performs two key actions. Dependency hoisting. It analyzes the dependencies of all packages within the workspace and installs them into a single, shared Node modules directory at the root of the project. This deduplicates common dependencies, saving disk space and ensuring that all packages use the same version of a shared library. Local package symlinking. It creates symbolic links in the root node modules directory that point to your local workspace packages. For example, if WebApp depends on UI library, and both are packages in your workspace, the node modules/UI library inside WebApp will be a symlink to the actual source code of your local UI library package. This symlinking is the core benefit of workspaces. It allows for a seamless development workflow where changes made to one local package are instantly reflected in other local packages that depend on it, without any need for publishing and reinstalling. Workspaces also simplify project-wide tasks, providing flags to run scripts across all packages simultaneously, e.g., npm run test, workspaces or PNPM, filter equals * test. This automation is what makes the monorepo pattern practical and scalable for modern JavaScript development. Conclusion. The Node.js package management ecosystem is a complex, layered system that has evolved significantly in response to the demands of modern software development. The journey from the simple conventions of early NPM to the robust, deterministic, and explicit systems of today is a narrative of an ecosystem learning from its challenges and progressively building more resilient tools. A candidate who can articulate this narrative demonstrates more than just technical knowledge. They exhibit an understanding of the fundamental principles of software engineering that drive this evolution. Mastery of this domain begins with the package.json file, understanding it not as a mere list of dependencies, but as a formal contract that defines a package's identity and its public API. The shift from the ambiguous main field to the powerful and encapsulating exports map is a testament to the growing need for stricter API boundaries and support for multiple module formats. Similarly, a nuanced understanding of dependency types, particularly the distinction between a dependency and a peer dependency, reflects an ability to reason about software architecture and plug-in ecosystems. The core tension between flexibility and stability is resolved through the interplay of semantic versioning and lock files. The package lock.json is the cornerstone of reproducibility, a critical artifact for both deterministic builds and supply chain security. The existence of distinct commands like npm install and npm ci provides developers with the explicit tools needed to manage this trade-off, using flexibility in development and demanding rigidity in production. The module resolution algorithm, while intricate, is a deterministic process. The ability to trace this process from core modules to path-based lookups and the recursive node module's walk is a vital debugging skill. This is further complicated by the common JS/ES module's duality, a leaky abstraction whose interoperability rules are a frequent source of errors and a key area of advanced knowledge. TypeScript's integration, particularly through the @types ecosystem and its module resolution settings, is a pragmatic and elegant solution to typing the untyped JavaScript world. Understanding the nuances of this integration, such as when an @types package should be a dependency versus a dev dependency, separates a practitioner from an expert. Finally, the broader landscape, including the rise of alternative package managers like Yarnberry and PNPM, and the adoption of monorepo patterns enabled by workspaces, shows that the ecosystem is continually striving for greater efficiency, security, and scalability. These are not just competing tools. They represent different philosophical answers to the fundamental problems of dependency management. Ultimately, a deep conceptual understanding of these topics is a powerful proxy for engineering maturity. It signals an ability to build, debug, and deploy complex systems reliably and securely. It is this level of insight that distinguishes a senior engineer in a competitive technical interview.